Guess what? We're talking about relationships again. Don't worry, I'll spare you the dating advice. I'm sure you're experts by now. Actually, today we're talking about relationships between cosine and sine around the unit circle. Now, keep in mind that we said all the ordered pairs around the unit circle fit into this cosine theta, comma, sine theta. In other words, the x-coordinate is the cosine of the angle, and the y-coordinate is the sine of the angle. So around our unit circle, remember that it falls around the origin and it passes through all of our quadrants. Now the quadrants of the coordinate plane, remember, start in the top right hand corner with 1 and move counterclockwise 2, 3, and 4. Also keep in mind that quadrant 1 has both positive x values and positive y values. In other words, the cosine and the sine are both going to be positive. Quadrant 2 can be found by reflecting all of these points here in quadrant 1 over the y-axis, which means the negative will now be on our x-coordinate. So we'll have negative positive here in quadrant 2, and down here in quadrant 3 are actually all the same coordinates as quadrant 1, but now both the x and the y are going to be negative. So this is our negative quadrant. And finally, quadrant 4 is the same thing as quadrant 1, except for all my values on my sine or my y-coordinates are now going to be negative. So I can take all of these coordinates here in quadrant 1 and reflect them over the x-axis to get all the points here in quadrant 4. All right, let's take a look at a few examples now. It says to find the cosine and sine values depending on the quadrants. In which quadrants are the sine positive? Well, keep in mind sine is my y-coordinate. Positive y's occur above the x-axis, so that's going to be quadrants 1 and 2. In which quadrants are the cosine positive? Well, again, keep in mind cosine is my x. X is positive to the right of the y-axis, so that's quadrants 1 and 4. Question 3 asks, if cosine theta is less than 0, that means it's negative, and sine theta is greater than 0, that means it's positive, in which quadrant is theta? So if I have a negative positive, I'm going to come to the left and I'm going to come up. So that's going to occur here in quadrant 2. All right, now here's a very important identity theorem that we learned, and it's called the Pythagorean Theorem, or the Pythagorean Identity Theorem. Now you guys learned what the Pythagorean Theorem is a long time ago. You learned that a squared plus b squared equals c squared. In other words, the square of the two legs of a right triangle and their sum is equal to the square of the hypotenuse. Well, this holds true for our unit circle as well, because keep in mind any point that I connect on the unit circle here is going to have a hypotenuse of 1, and the two legs are going to consist of the coordinates. Cosine theta is going to be my x, so here's cosine theta, and sine theta is going to be my y. In other words, the distance off of the x-axis is going to be my sine of that theta, and the distance along the x-axis from the origin is going to be my cosine theta. So my two legs are cosine theta and sine theta. When I square them and add them together, I should get the hypotenuse of that right triangle, which is 1. All right, let's jump into some examples today using that same diagram. It says, suppose that the angles formed by the segment and the positive x-axis is 28 degrees. In other words, our little theta here is 28. We want to approximate the coordinates of point C to the nearest thousandths. So we're going to take the cosine of 28 degrees and let that be our x-coordinate, and the sine of 28 degrees, and that will be our y-coordinate. So using our graphing calculators, we will tap in our cosine of 28, and that will give us our negative, now here's a very important thing I just remembered here as I typed in cosine 28. On your graphing calculator, we do need to make sure that our mode is set to degree. So come down here to the third line, over to degree, and go ahead and press enter. And now you can go back and hit your cosine 28. And now you'll have your 0.883. And now we'll do sine 28. And that will give us our 0.469. So our coordinates here should be our 0.883 and 0.469. All right, now it says verify your coordinates in part A that satisfy the Pythagorean theorem identity. So again, remember the x leg of this right triangle, if I form this right triangle, should be my 0.883, and my y, or my other leg of that right triangle, should be 0.469. Whoops, 0.469. So we're just going to follow that along. Cosine theta squared is 0.883 squared, plus sine theta squared is my 0.469 squared. And we should verify that that is equal to 1. So let's go back to our graphing calculator. We're going to type in 0.883 and square that. Add that to 0.469 squared, and we should see that that's very close to 1. In fact, it is, so we say, yep, it fits our Pythagorean identity theorem. All right, example 2 says to use the inverse cosine function to find theta, then use theta to find the y-coordinate. All right, so if I take a look here, I see that point P is on my unit circle. I don't know the angle off of the x-axis, but I know that the cosine is equal, the cosine of theta is equal to 0.8. So if I take the inverse cosine of both sides, I can get rid of that cosine, and I'm going to be left with my theta is equal to inverse cosine of 0.8, and that will give me my angle measure. So let's check out what that is. If we take our second function, cosine of 0.8, we'll get our angle measure of 36.9 degrees. So we'll say theta is equal to 36.9. Now, if I know that that theta is equal to 36.9, I can now find my y-coordinate by taking the sine of 36.9 degrees. And let's go back to our calculator here, and we'll say sine 36.9, and that's going to be equal to 0.6. So there's our y-coordinate. All right, now in example 3 it says to show why the cosine of 252 is equal to the negative cosine of 72. So take a look at your unit circle here, and this one's not provided on your notes, so go ahead and take a second to scratch that out. And keep in mind that this x-coordinate here is the cosine of theta, and my y-coordinate is the sine of theta. So it says to show why cosine of 252. So if I come here, this is 90 degrees, here's 180. 252 should lie somewhere down here in my my third quadrant here. So if I just go ahead and connect that point here, I'm going to write out cosine of 252 degrees. Now it says show why it's equal to the opposite value of the cosine of 72. Well, remember, these coordinates down here in my negative quadrant are going to be the same as my positive quadrant. However, they're just going to take on the opposite values. So 72 degrees is actually going to be about right up here. And if I connect that, this is my cosine 72. So remember, this value of 252 can really be found by taking the same cosine value as if I were to take 252 and subtract that from 180. So when I take 252 and subtract from 180, I do actually get 72 degrees. In fact, all of these coordinates here in my third quadrant can be found by taking 200, or whatever their angle is, that theta, and subtracting it from 180. And whatever that result is, if I take that opposite value, then it will be the same, or they'll be equivalent. All right, let's just show you on a graphing calculator here. That will make a whole lot more sense. So if I take my cosine of 252, you see that that's equal to negative 0.309, and now I'm going to take the opposite value of cosine 72, and you can see that's also negative 0.309. So all values that lie in that third quadrant, all these values here in the third quadrant can be found by taking their angle measure and subtracting them from 180. And whatever that value is, you take the opposite of that cosine or sine. Okay, so example 4 says, using the fact that cosine 78 is equal to 0.208, find an angle theta larger than 360 such that cosine theta equals 0.208 again. Well, keep in mind that cosine of 78 is my x coordinate at 78 degrees. So if we sketch out our little unit circle here, here is about 78 degrees. Now we want to find something larger than 360 where my cosine is also equal to 0.208. So I'm going to have to come around one full complete turn. Here's 360 degrees. And then if I go an additional 78 degrees more, that's 360 plus 78, I will come back to that same point. In other words, the cosine of this angle, which is the sum of 360 plus 78, should also be equal to 0.208. So let's do that. Let's take 360, add our 78. When we add those together, we get 438 degrees. So we should say the cosine of 438 is also going to be equal to 0.208. You can confirm that on your graphing calculator. All right, one more example for today. It says suppose the plane is at an altitude of 3,500 feet and the angle of elevation from the airport to the plane is 29 degrees. What is the horizontal distance between the plane and the airport? Round to the nearest foot. All right, let's start off by sketching out our picture here. Here is our beautiful airplane flying. Oh boy, that's a terrible airplane. But anyways, it's got an altitude of 3,500 feet. So remember, altitude is your vertical distance to the ground. We got an angle of elevation to the airport of 29 degrees. So here's our airport. What is the horizontal distance between the plane and the airport? So again, now we're talking about horizontal distance, so that's like ground distance here. So this is what we're looking for. We have this angle of elevation, we know our opposite, and we're looking for our adjacent. So this is going back to SOHCAHTOA. Opposite and adjacent is going to apply the tangent ratio. So I'm going to say the tangent of my angle measure is equal to my opposite over my adjacent, which is what I'm trying to find. So from here, you guys know how to solve this. We're going to multiply both sides through by x. That gets rid of it on this side. Then I got to divide both sides by tangent 29. So in the end, I will have this horizontal distance x will be equal to 3,500 divided by tangent 29. And when I do that on my calculator, I should get a distance of 6,314 well, that's it. 6,314 feet.